Hello, this is Mr. Manley. I'm going to look at some trigonometry problems from an introductory chapter on trigonometry. The first one here is, as you can see, angular and linear speed. I'm just going to run through these pretty quickly without too much commentary, just showing you exactly how I would do the problems. So for this problem, I have a Ferris wheel with a diameter of 48 feet and a 4 revolutions per minute. For part A, I'm being asked for radians per minute. So all I'm thinking about is that I have revolutions per minute, and I want to try and get that converted to radians per minute. So I have 4 revolutions per minute, and I've already got minutes, see, per minute on both of these, so I don't have to do anything with that. I need to get the revolutions to cancel, and I need to get radians in the numerator. So if I know how many radians per revolution there are, the problem will be finished. And there are always 2 pi radians per revolution. That goes for any problem, any scenario. There are always 2 radians per revolution. So if you ever need that relationship, you've got it, and it's the same every time. Now that I've got that, the revolutions cancel, and we are left with 8 pi and radians per minute, and that problem is done. In the next one, or the next part of the problem, I'm looking for linear speed in miles per hour. So I'm either going to use the 4 revolutions per minute that was given, or I'm going to use the 8 pi radians per minute that I found. I want to convert one of these to miles per hour. So let's look at how this first one might look. I have miles. I need miles per hour. Now, last time I had minutes and minutes, right? This time I have minutes and hours. So let's do that conversion. That's going to be easy enough to do minutes over hours. So minutes will cancel with minutes if I know how many minutes there are per hour, and of course we know that there's 60 minutes per hour. So now I've got revolutions. At this point I'm going to have revolutions per hour, but I need miles per hour. In order to get miles per hour, I would need to know how many miles there are per revolution. We are going to be able to figure this out if we know the circumference, right? So let's go down here. We'll go ahead and get rid of this, radians per minute. We're not going to use that. So I'm going to do the circumference of this is equal to 2 pi r, which is 2 pi times what was the radius. Go back here, and we see the radius, or the diameter is 48 feet, so the radius is 24 feet. So I'm going to go 24, and that'll be 48 pi feet. I'm not going to use a calculator on this. I'm just going to keep it as pi for right now. So 48 pi feet. Well, you see this? I have feet, and I want miles. So I'm going to just do that conversion down here, and then this is 48 feet per revolution, right? 48 feet, and that's the circumference, which is 1 revolution. So I have feet per revolution. I'll go ahead and change that to miles per revolution, and then I'll pop it in up here where I need it. So I'm going to go times how many miles are there per foot. I believe there's 1 mile for 5,280 feet. And then down here, the feet will cancel with the feet, and that leaves me with miles. So I'm going to make a little space up here, and I've got 48 pi over 5,280 miles per revolution. And let's see what cancels here. The revolutions here cancels with the revolutions here, and that leaves me with miles per hour. So all I need to do now is take these values here, this 4 and this 60, 48 pi, and just key that into a calculator, and I'll have my miles per hour. I'm not going to key that in. You can do that easily enough, and we don't really need to. We just need to see how the calculation goes. Next problem. Let's see, this says evaluate expressions with sine and cosine. So this is we're given a theta here. Theta is equal to pi over 3. And then we're being asked to, essentially, you see the thetas here. There's theta, there's theta, there's theta. So we're just going to be plugging this in and then using the unit circle is all we're doing on this problem. So I'm going to go for A. I've got cosine of pi over 3. That's theta over 2, which is cosine of pi over 6. Now I'm going to go to a unit circle, and on a unit circle I'm going to go to pi over 6, which might be hard for you to read, but it's right there. And what did we want? We wanted cosine. Well, cosine of theta, the cosine of an angle theta, is equal to x over r. And in our case, r is 1, because that's what a unit circle is. It's a circle with a radius of 1. So the x-coordinate here at pi over 6 is right there. It's rad 3 over 2. And that's it. Cosine of pi over 6 is rad 3 over 2. Moving to B, I've got cosine of negative pi over 3. So all I'm doing is I'm plugging in this value of theta for this theta here. And then that's cosine of negative pi over 3. Now go to the unit circle. On the unit circle, I find pi over 3 here. And again, it's still cosine. And cosine, as we saw earlier, here is the x value. So on a unit circle, the x value at pi over 3 is here, which is 1/2. Oops, and I just noticed that we have this is a negative pi over 3. So I went to pi over 3. So let's go back to our unit circle. Okay, negative pi over 3 is this way. So although in the unit circle this says 5 pi over 3, we're going this way, and negative pi over 3 is coterminal with that. And then taking the cosine, the x-coordinate there, it's still 1/2. So this is 1/2. And then finally, this cosine squared. Now, cosine squared theta is the same thing as this. It's the same thing as doing cosine of theta squared. These are synonymous. So doing our substitution, cosine pi over 3 squared. From our unit circle, we already had that cosine of pi over 3 is 1/2. So cosine of pi over 3 is 1/2 squared, and that's equal to 1/4. Next problem, values of trig functions given info, and this is not a unit circle. We want to think about a circle, but this circle does not have a radius of 1. What do we know about this circle? We know that point 512 is on it. So if I just make up a point really here, if I go 5 and then up here, so say I'm go here to that, and I say, all right, well that's x is 5 and y is 12. Does that make sense? I'm just going to a coordinate 5, 1, 2, 3, 4, 5, and then I'm going to something bigger than 5, right? More than twice as big as 5. And then I'm saying that's where that point is. Well, if that were the case, what would the radius be? So the radius is here. I'm going to make a right triangle. So I've got a right triangle with this side 5 and this side 12, and that's a special right triangle, right? So the radius is 13. And then I can take this and I can say I want cosine theta, which is x over r. Remember that formula? Cosine theta is equal to x over r. So our x in this case is right there. It's 5. And our r is right there, 13. And then the cosecant of theta, you can look at your formula sheet and see that that's r over y. And we know r is 13. And we look here and we see y is 12. And then finally tangent theta, right off the formula sheet, is y over x. And that's just 12 over 5. And I think are we going to do one more? Yeah, just one more problem. This problem is asking us for a quadrant. There's some angle theta, and I know that that angle theta has a sine value that is negative. Now, something that you get in class sometimes, and I know if you're in my class you've got it, is that all students take calculus. A, S, T, C. S is for sine, T is for tangent, C is for cosine. So when I see that sine of theta is less than 0, that means that the sine value of theta is negative. Now what this A means, all of them are positive if the angle is there. This S means sine is positive if the angle is there. And by the angle, we mean the angle starts on the positive x-axis and rotates around like this. So it rotates in that direction. Okay? So I just want to go sine of theta is less than 0, and I'm going to check off, well, that means it's negative, which could be here in this quadrant or in this quadrant. And then when I look at tangent of theta is greater than 0, so it's positive. Well, everything is positive here in the first quadrant, so it could be here. And tangent, that T means that tangent is positive if the angle is in that quadrant, so it could be here. So theta has to match both possibilities, or both of these conditions need to be met for sine theta less than 0 and tangent theta greater than 0. Therefore, we are in this quadrant. And hopefully you know how the quadrants are numbered. The quadrants are numbered 1, 2, 3, 4. That's how they're always numbered. So if we're in this quadrant, the answer to this question would be that the angle theta is in the third quadrant. So I hope that helps with a couple of the more challenging problems. And that's all I have for today.